Good evening, everyone, and welcome to the 13th Annual Stephen H. Schneider Memorial Lecture. This year's lecture is organized by Students for a Sustainable Stanford and is sponsored by the Stanford Woods Institute for the Environment. We are your hosts for the night. My name is Annabelle Choi.
And I am Sydney Dever Mendenhall. Before we begin, please silence your cell phones. This lecture is held in honor of Dr. Stephen H. Schneider, who is a leading expert in climate science and a crucial voice communicating research to the public. Dr. Schneider was and continues to be a hugely influential figure for the field of climate research, climate policy, and outreach. As a leading voice in the fight against climate change, Dr. Schneider served as a consultant for each president, from President Richard Nixon to President Barack Obama. As a beloved professor, Dr. Schneider has also left an indelible mark here at Stanford University. It is undeniable that he dedicated his life to his students and to the world around him.
We are here tonight thanks to Professor Terry Root. On top of a long list of scientific awards and honors, Dr. Root has dedicated her life to improving the accessibility of scientific information. We would like to extend a special thanks to Dr. Root for her incredible support and guidance for this event. Thank you so much, Dr. Root. All right. Now we will begin our program with a video honoring Dr. Schneider's life and work. Thank you.
The climate is caused by an interaction among the energy stored in oceans and glaciers, these big masses of ice up at the poles, and that which comes in from the sun. That's where pollution comes along, because it's not just something that makes your eyes hurt and maybe shortens your life, but it can actually interfere with the energy that comes from the sun and that which goes back out.
We started out saying sort of, Houston, there's a problem in 1990. Then we said, not only is there a problem, but the humans are part of it. In 1995 and 2000, Terry Root added, and plants and animals are in it too. And now we said, not only is there a problem, but it hurts the poor more than the rich. It hurts the vulnerable in Hurricane Alley and in high mountains and in the Arctic and in Mediterranean climates like California more than others.
The absolute best we're going to get away with is about 2 degrees above pre-industrial, which the EU defined as dangerous climate change, because that increases the severity of drought, flood extremes, heat waves, intensified storms, fires, and species extinction. So it's absolutely urgent that we don't go much above 2 or 3, which scares me a lot. And on our current path, we are going to be lucky to hold it to 3.
The media is trained primarily in political reporting.
Here's my thing with it. There's always been extreme weather.
That's where the hoax is, and that's where it harkens to medieval witchcraft. This is all predicated on getting rid of capitalism, isn't it?
Where would those kids be if we did not have the fossil fuel era?
But science is not bipolar. It's not end of the world and good for you. Science is not dichotomous in 2 separate groups.
Stephen has been just an incredible wealth of inspiration and information for those of us at Stanford who are working at the interface of environment and energy and natural resources.
I mean, a student group came in this office about 2 years ago and said, we're going to go in and demand of the president that Stanford set up the following sustainability agenda. And I said, whoa, hold on. I think you should tell him that you want Stanford to do that. But why don't you first go in and tell the president what you yourselves have done, and then ask, how is Stanford as an institution going to match you? And they did that. It was very effective. The president got a sustainability group energized. So you've got to show that it's not your fault, but that we're part of it, and we're doing our bit. We can't do it all. We need you.
It's that little ball of water spread thinly over the earth that makes our civilization, everything we care about, possible. No ocean, no life. No ocean, certainly no us.
Those cycles of hydrology, those cycles of carbon, those cycles of nitrogen
need intelligence and care, and they need responsibility.
Photosynthesis is like the OG of carbon sequestration, right? And wetlands can absorb, 5 times more carbon in their soils than a tropical rainforest.
I like to note that the biological diversity of the world is an immense genetic library, which we are burning down before we've even cataloged the books, never mind reading them.
So what I'd like to do is take you guys through a little bit of history of growing power, of how we built our food system that can help heal communities.
What's possible one day is certainly not bounding me for tomorrow. And if I feel bounded by what's required, I'm missing real opportunities for economic growth, for sustainability, and for environmental protection as well.
We're not talking about incremental change or going after low-hanging fruit. We're talking about the hard stuff. We're talking about transformative change.
The accumulation of global warming pollution from human activities now in the planet's atmosphere traps as much extra heat every 24 hours as would be released, the scientists tell us, by 400,000 Hiroshima atomic bombs going off every day on Earth.
He had the language, he said, pay attention to the language. Climate change, sustainability, hypoxia, dead zones, turning up the thermostat, melting out polar caps. And so what happened over 16 years, the language got louder and louder, just as he predicted.
Scientists should speak up for their science because it's an obligation, in my opinion, that every person should leave the world better than they found it. And if you're a scientist who has some special knowledge about a piece of the world, and you think that knowledge needs to be joined together with that of other people to help us either take advantage of an opportunity or prevent a really bad problem, then not to say that means you're really shirking your obligation to take the opportunity of your luck at really having an understanding. You've got to do it. And you realize there'll be some people who are going to oppose you for doing it, especially those who might be losers if we have to change the way we do things and we have to get out of the status quo. And you have to be prepared to take that because that's exactly what happens. You never make change easily. The old cliche is you can't make the omelet until you crack the eggs.
Climate scientists like Dr. Schneider have given us a huge wealth of knowledge and tools to equip us against climate change. From the cars we drive to the clothes we wear, we begin to see that every part of our everyday mundanity can contribute to huge impacts around the world. With this, it is my pleasure to introduce you to our 13th annual Schneider lecturer, Dr. Ben Santer.
Ben Santer retired from Lawrence Livermore National Lab in 2021 after 30 years of work at the Program for Climate Model Diagnosis and Intercomparison. He served as the lead author of Chapter 8 of the historic 1995 second IPCC report, which concluded that the balance of evidence suggests a discernible human influence on global climate. Since then, Dr. Santer has done groundbreaking research on identifying human fingerprints in many different observed climate variables, such as atmospheric temperature and water vapor, ocean heat content, and sea surface temperature in hurricane formation regions.
Dr. Santer has received a number of awards for his research, such as the MacArthur Fellowship in 1998, a membership in the U.S. National Academy of Sciences in 2011, and the John J. Carty Award from the NIS in 2024. He also cares deeply about climate communication and has been an outspoken advocate for improved climate policy. Dr. Santer was also a dear friend of Dr. Schneider, so we are especially honored to have him here with us tonight. So, without further ado, please join me in welcoming our speaker, Dr. Ben Santer, to the stage.
Thank you, Sydney. Thank you. Good evening. It's really important to honor your friends. Steve was my friend, and I'll try and honor him tonight at the end of my presentation. First, a little bit about myself. So, I'm a US citizen, but I grew up in Germany and in the UK. My life's work has been in fingerprinting the climate system, trying to disentangle human and natural effects on climate. My hobby is rock climbing, and even as an old dude, I get to go rock climbing with my son. He has all the responsibility now, and my job is just to try and follow him up stuff like this. This is at the beautiful, stately Pleasure Dome in Tuolumne Meadows. If you haven't been to Tuolumne, go there. It's worth a visit. Part of my job tonight is to give you some sense of the arc of history here. For me, this arc of history started in 1990 with the first assessment report of the Intergovernmental Panel on Climate Change. The IPCC has the job of advising the governments of the world about the physical science of climate change, the likely impacts of climate change on things we care about, human health, agriculture, many other things, and possible mitigation and adaptation strategies. Their first report concluded that the jury was out, that it was too early in 1990 to say whether we could or could not formally identify a human-caused global warming signal. Sydney and Annabelle mentioned the second assessment report in 1995. Fortunately or unfortunately, whichever way you look at it, I was the convening lead author of a key chapter of that report, Chapter 8, that dealt with detection of climate change and attribution of causes. And after 1.5 years of work, our bottom line finding was the 12 words that you just mentioned. They're forever engraved on my memory. The balance of evidence suggests a discernible human influence on global climate. Why was that important? I would argue that it was the first time that the international scientific community spoke with one voice and said formally, we can identify a human-caused climate change signal. It's emerged from the noise of natural climate variability. I spent arguably the next 30 years of my life defending that finding and the process by which it had been reached. I was investigated by Congress. There were calls for my dismissal with prejudice from my position at Lawrence Livermore National Lab. It was rumored that I was about to be indicted by the Hague International Court of Justice for, quote, falsification of international relevant scientific documents. It was a bad time, but I learned a lot of valuable lessons, and one was the lesson that Steve gave us at the end, that if you're a scientist, you have some responsibility to defend the hard-fought scientific understanding that you and your colleagues have reached. What's the point of being a scientist if you're unwilling to stand behind the science that you and your colleagues have done? Well, that second assessment report, although controversial, was followed by reports that upped the ante, that tried to qualify and quantify the size of the human effect on climate. Unlike our wimpy balance of evidence suggests finding, they introduced this likelihood language and said how much, in their opinion, of the observed warming was due to human-caused greenhouse gas increases. This was in 2001, the third, in 2007, the fourth, in 2005, the fifth assessment, and you can see in yellow there how that likelihood language is ratcheting up until October 2021, the sixth assessment report of the IPCC that used this extraordinary word unequivocal. It is now unequivocal that human fingerprints are all over the climate system, land, ocean, and atmosphere. Why? Why has there been this arc of history? What explains it? How did we get from the jury is out in 1990 to unequivocal human fingerprints on the climate system in 2021? I would argue that there were many drivers of this progress. Back in 1990, we had only a few computer models of the climate system. They were relatively primitive. They had primitive representation of the ocean. They weren't the full Earth system models that we have today, with many, many different components of atmosphere, oceans, sea ice, biosphere, communicating with each other, atmospheric chemistry in there. Now, for the 6th assessment report of the IPCC in 2021, we had nearly 100 different climate models from countries and research institutes around the world. Back in the early 1990s, we thought that human-caused changes in heat-trapping greenhouse gases were it. We didn't really think too much about other things that humans were doing to the climate: sulfate pollution, soot aerosols, deforestation. And over time, there was a better understanding of those factors, both human and natural, changes in the sun's energy output, changes in volcanic dust, and people began to put those factors, human and natural, into computer model simulations of historical climate change. Back in 1995, at the time of the discernible human influence finding, we had less than 20 years of satellite measurements of temperature change in the atmosphere. Now we have over 45 years. Those longer records were critical in informing us about the size and the rate and the patterns of climate change. That too was important in making this progress. I would say another thing that was important is crowdsourcing. Back in the 1990s, individual computer modeling groups were looking at their simulation output. They often were holding on to that output for years before sharing it with the rest of the community. And it was recognized that that wasn't good enough, that at a time when many people were going to pay attention to the results from computer models, we had to do a better job evaluating them, comparing them, diagnosing systematic errors in them, trying to remedy those errors. And that couldn't be the purview of one group alone. The most effective way of doing that was by opening up the diagnosis of models to the entire climate science community. That too was influential. We had infrastructure, things like the Earth system grid, for sharing large volumes of climate model simulation output, satellite data, analysis software very efficiently, so that from the comfort of your own office, you can interrogate petabytes of simulation output, do statistics across models, look at uncertainties and projections of future climate change. That too, I would argue, was crucial to scientific progress, to this arc of history. And finally, this consilience. We had longer observational records, we had better models, we had more models, we had better observational data, and we had fingerprint methods, which is what I'm going to spend some time telling you about now. Consilience. E.O. Wilson had a book by this name. It's defined as the principle that evidence from independent, unrelated sources can converge on strong conclusions. And that's part of this arc of history. We had basic theory a long time ago about what increases in greenhouse gases might do to our planet's surface temperature and atmosphere. We had data that we started collecting from space in the late 1960s onwards that gave us the ability to transcend local perceptions of climate to truly global, to understand global changes in temperature and moisture and clouds. We had models that were part of this consilience and pattern recognition methods. And I'll give you examples of some of these things. So this gentleman, Suki Manabe, was at the Geophysical Fluid Dynamics Lab, a NOAA lab, for most of his scientific career. And back in 1967, he published this paper with a somewhat unprepossessing title, Thermal Equilibrium of the Atmosphere with a Given Distribution of Relative Humidity. Suki and Dick Weatherald used a relatively simple climate model that just looked at global mean changes at different levels in the atmosphere. And what they did in this simple model is they increased atmospheric CO2 from 150 to 300 to 600 parts per million. And as they did that, they saw that in this simple model, heat was more effectively trapped in the lower atmosphere, the troposphere, and the upper atmosphere cooled. And that cooling got larger the higher up you got above the Earth's surface. Critical point here, this was a prediction. This predates the satellite era. We really didn't have the measurements of temperature change in the upper stratosphere to verify whether this prediction was correct or not. We had some weather balloons, but they burst above about 20 to 25 kilometers. They didn't have the structural integrity to get up into the stratosphere. Was Suki Manabe right? He was. These are beautiful measurements here. These are satellite measurements of the microwave emissions of oxygen molecules. And we've made these measurements from NOAA polar orbiting satellites since the late 1970s. And what they show is exactly what Manabe predicted. This cooling of the stratosphere, with cooling getting larger the higher up you go above the Earth's surface, and warming of the troposphere, with the largest warming of the troposphere over the Arctic, where we've seen this profound decrease, roughly 50%, in the extent of Arctic sea ice over the last 45 years. Part of consilience is pattern recognition methods, and that's where this gentleman comes into it, Klaus Hasselmann. Klaus, together with Suki Manabe, was one of the recipients of the 2021 Nobel Prize for Physics. Manabe won for climate modeling and for insights into climate change and climate variability. Hasselmann won in part because of his work on pattern recognition methods. What did he do? He recognized back in the late 1970s that you couldn't just look at climate change simulations at individual grid points, which is what people were doing up to that point. You had to take a step back and look at patterns of climate change. And if you did that, then you had a better chance of disentangling global scale human effects on climate from much smaller scale natural variability. And I'll show you some examples of that later. So Hasselmann's thesis was, and here we're looking at slices through the atmosphere, and we're looking at model simulations where in model world, you can just change one thing at a time. And that's what was done here. Scientists at the National Center for Atmospheric Research just changed solar energy according to our best understanding of how the sun's energy output actually changed over the 20th century, or volcanic aerosols, or human-caused changes in greenhouse gases, human sulfate pollution, human-caused changes in ozone, in the troposphere, in the stratosphere. I won't get into the details of these different fingerprints. The point is they're different. What Hasselmann recognized was that patterns have discriminatory power. We can use this kind of information to disentangle the observations and figure out how these different influences are affecting Earth's climate. It was a profound insight. I'll give you an example of what I mean. This is from a paper that my colleagues and I published a couple of years ago, where given measurements of atmospheric temperature that now go up to 50 kilometers above the surface, we could look at the very region of the atmosphere where Manabe predicted in 1967 that we should see a big human influence on climate. We could go after that stratospheric cooling signal, that human-caused stratospheric cooling signal. What we found was, I'll quote, extending fingerprinting to the upper stratosphere with long temperature records and improved climate models, so models that went high enough to be able to look at what they were doing in the mid to upper stratosphere, means that it is now virtually impossible for natural causes to explain satellite-measured trends in the thermal structure of Earth's atmosphere. Here's the kind of thing that we did. So one of my postdocs persuaded me about 5 or 6 years ago to start using Matplotlib and Python. And I'm very indebted to him for extending my scientific career by at least another decade by teaching me these things. So these are satellite measurements of atmospheric temperature from these NOAA polar orbiting satellites. And we're going to march forward in time from 1986 through to the present, through to 2024. And you can see in each year what's happening to atmospheric temperature. Red is warming, blue is cooling, and over time, I'm showing not every year, but every 3 years, what's happening is the vertical structure of atmospheric temperature is becoming more similar to the human fingerprint in response to increases in greenhouse gases. See the last year, 2024, and the year before that, we're seeing that pattern of cooling of the stratosphere, warming of the troposphere set up, which is in accord with our best model predictions of the changes we should see in response to human-caused increases in greenhouse gases. And what you can do is you can calculate some measure of pattern similarity between the searched for human influence fingerprint and the actual data. And this pattern similarity time series shows you what you can see with your eye, that over time, the satellite data are becoming more similar to the searched for human influence fingerprint. So there's a trend in this pattern similarity time series. The science question is that trend significant? Could we have gotten a trend like that just by chance, just by the random vagaries of natural climate variability? So we look at that routinely by taking the same fingerprint. Here's the correspondence that you see, that red line from the previous figure, the correspondence between the data and the human fingerprint maps here in trend space over roughly 40 years. And now we're going to do the same thing with patterns of natural climate variability from many, many thousands of years of so-called control simulations, when climate models are run with no changes in greenhouse gases, but just give you that rich intrinsic variability on monthly, decadal, multi-decadal timescales. And we're going to step through these 300 years at a time. I have many thousands of years of data that we're using for this exercise here. And what you can see immediately is there's some warming, there's some cooling, but these patterns are small scale. They don't show simultaneous warming of the lower atmosphere and cooling of the upper atmosphere. So when you do the same thing that we did with the actual satellite data and compare these control runs with the human influence fingerprint and calculate the same measure of pattern similarity, and I'm showing the first 400 years here, and you calculate trends over the same 39-year period that we used for looking at the actual satellite data, you get a distribution of natural trends. And the key point here is that the figure on the left and the figure on the right have the same range in the y-axis. So what this tells you is that the correspondence, the pattern correspondence between the fingerprint and the satellite data is far, far greater than between the fingerprint and natural climate variability. And that's the kind of thing you see here. The blue distribution is what chance gives you, and the red line is what we got when we compared the fingerprint with the satellite data, which enabled us to say that it was virtually impossible to obtain this fingerprint match that we got for the satellite data by natural variability alone. Why? I think this is part of the reason why. The human fingerprint gives you this large-scale warming of the lower atmosphere, cooling of the upper atmosphere, cooling getting larger the higher you get above the Earth's surface. Natural variability doesn't do that. It gives you small-scale, noisy patterns that are associated with things like El Niños and La Niñas, or something in the stratosphere called the Brewer-Dobson circulation. It can't do this kind of thing, coherent warming low down and cooling up high. This just shows you that the latest, greatest model simulations from so-called phase 6 of the coupled model intercomparison program all show you qualitatively similar thing. When you increase greenhouse gases, you get warming low down, cooling of the upper atmosphere. The satellite data in the lower right panel show a very similar thing. One of the criticisms of the discernible human influence finding back in 1995 was you scientists are just looking at surface temperature. If there really is a human-caused climate change signal lurking in observations, convince us. Don't just look at surface temperature. Look at the vertical structure of atmospheric temperature change. Look at moisture. Look at many different things. And that's what the community did. We went far beyond surface temperature only fingerprint studies and atmospheric temperature and the height of the tropopause, the boundary between the troposphere and the stratosphere. People looked at atmospheric water vapor. They looked at ocean heat content, the depth of snowpack in mountainous regions in the western US, runoff from major river basins, cloud properties, cloud height, cloud location, cloud albedo. They looked at ocean surface temperature changes in hurricane formation regions, hurricane breeding grounds, the seasonal cycle, whether humans were affecting the march of the seasons themselves, both in the troposphere and in the ocean. Drought properties, looked at measures of aridity, a number of different measures of aridity. And the key thing is that changes in these and many other variables were internally and physically consistent, which is powerful if you're a scientist. They're monitored independently. These are research groups around the world looking at these changes. And they're using fingerprinting. They're using pattern analysis to confront models with observations. And the message in each case was nature can't explain what we've monitored and observed. I'm retired, as Sydney and Annabelle mentioned here, but I'm not really retired. Probably won't be a surprise to those of you who know me. I'm failing Retirement 101 pretty miserably. And one of the things I've been obsessed about, and I think obsessed is the right word here, is a simple thought experiment. So indulge me for a moment, if you will. Imagine that we live in a world in which we have satellites back in 1860. And those satellites enable us to monitor changes, global changes in atmospheric temperature with the same accuracy as today's satellites. Imagine also that we started monitoring in 1860 and went forward for about 40 years until the end of the 1800s. And imagine that for this simple thought experiment, we're looking at model simulations that are driven by changes in carbon dioxide and other greenhouse gases that are reasonably accurate representation of the changes in greenhouse gases that actually happened in the real world. How do we know some of those changes? Primarily from ice cores. That's the information that was used for these simulations of historical climate change in the latest phase of the so-called CMIP-6 Climate Model Intercomparison Program. So this is my little thought experiment. And if you look at the first 40 years, the CO2 changes are small. The increase from 1860 to 1899 is only about 10 parts per million, so far smaller by a factor of about 2.5 than the changes that we've seen over the first 25 years of this century. But nevertheless, the surprising message from this work was if you looked at the stratosphere, where Manabe predicted this very strong human-caused signal of stratospheric cooling, you see these interesting ripples, roughly 11 years long. So these are the impacts of the solar cycle, the 11-year solar cycle, that are affecting the temperature of the stratosphere. That big spike there is the eruption of Krakatoa in 1883. Krakatoa, big eruption, injected a lot of sulfate aerosol into the stratosphere, and that warmed the stratosphere and cooled the troposphere. the bottom line is that in this thought experiment, using the latest, greatest climate models, which is what you see here, we could have known by about 1885 that something unusual was going on, that the cooling we were monitoring couldn't be natural. So if you look at the longer sweep of time, from 1860 through to the present, you can see in these three layers of the atmosphere, the lowest panel is from 25 to 30 kilometers above the surface, the upper from 40 to 50 kilometers above the surface. Look at the richness of the information in there. Those ripples, that's the 11-year solar cycle again. The big green lines are volcanic eruptions. Krakatoa, Santa Maria, Nova Rupta, Agung, Fuego, El Chichon, Pinatubo, and you can see that they're warming the stratosphere. Again, the bottom line here is that if we had started monitoring with satellites back in 1860, we would have been able to say with a high degree of confidence by about 1885 that humans were affecting global climate. So this is the conclusion from this new work that I'm doing, that a human-caused stratospheric cooling signal would have been identifiable by approximately 1885 before the advent of gas-powered cars. Our results suggest that a discernible human influence on atmospheric temperature has likely existed for over 130 years. Now, a different thought experiment is, would it have made a difference? Would humanity have embarked on a different energy use pathway if we had known back then that our actions were changing the global climate? And I'm not the right guy to do that thought experiment, but it's an interesting one to think about. Would it have made a difference? I'm now going to pivot to talking about Steve. I love this little, these two sentences here. A mind full of questions and a teacher in my soul, and so it goes. So that's from Pearl Jam, from Eddie Vedder. And why am I using that? Because this was Steve. Steve had a mind full of questions. Here are some of them. How are human activities influencing Earth's climate? How will human-caused climate change affect living things? Something that he and Terry were profoundly interested in and made important contributions to. How can we make smart decisions about the future of the planet in the face of key scientific uncertainties, in the speed and size of projected changes in climate over the 21st century, in the geographical and seasonal details of these changes? And he had a teacher in his soul. He taught us in many different ways through his scientific papers on dozens of different subjects. I reviewed his CV today and spent probably about 2.5 hours just marveling at the depth and breadth of the contributions that he made through his papers, some with people in the room, like Mike, and with Terry, profound insights into the effects of climate change on ecosystems, into probabilistic assessments of climate change, emissions targets, geoengineering, different policy options for managing Earth's climate. Amazing depth and breadth. Another part of the teacher in his soul was his public talks. Steve gave hundreds of public talks around the world to anyone who would listen to him, and sometimes even to people who wouldn't listen to him. That was a really important way of teaching and inspiring. The teacher in his soul was also through his books. In addition to his scholarly papers, he wrote a boatload of books about every aspect of climate change, science and policy. His last book, Science is a Contact Sport, about some of the difficulties climate scientists face in communicating about climate change, difficulties that we still have today. The Genesis Strategy, one of his first books, Climate and the Coevolution of Life. He taught, as Annabelle and Sydney mentioned, through his advice to 8 administrations, from Nixon through to Obama. And here are just some images of Steve providing that sage advice. And I had the extraordinary privilege to be in this picture here to provide advice to the now defunct House Commission on Energy Independence and Global Warming, where Steve and I first encountered the claim that global warming had stopped in 1998. And Steve taught through his service to IPCC. He was involved in all IPCC assessments up to his untimely passing. And here are pictures of Chris and Terry and Steve and others, Michael Oppenheimer here. So many ways of teaching. And through climatic change, arguably one of the premier journals of our field that is still going strong. I just thought I'd read to you a few tributes to Steve, some from people in the room here, some from people you may not know, that were written after Steve passed away. Paul Ehrlich wrote this: "A giant in his field, a wonderful friend, a hero, and more. Mike, I realized that I had met a brilliant scientist who possessed a unique talent for both explaining complex issues and encouraging others to care about them. Miles Allen, one of the luminaries in fingerprinting, Steve believed passionately in evidence. Bud Ward from the Yale Forum on Climate Change. Now we have one less giant among us and one less truly exceptional voice embodying both scientific excellence and extraordinary communication skills. Jim Hansen, he is irreplaceable. Climatic change was Steve Schneider. And Steve was an exceptional scientist. Steve was as tough as nails. Susan Solomon, Steve said something that I'll never forget, that leaders in science have 3 I's: intelligence, innovation, and integrity. We've lost the truest leader we could have wished for, but remembering the 3 I's, as much as we lesser mortals can, will help us keep him in our thoughts and will enrich our lives." Here are some personal lessons, finally, that I learned from Steve. And I hope some of these lessons resonate, particularly with the students in the room. Don't engage in science by eminence of position. Trust me, I'm a scientist at a big national lab, or I'm a famous professor. No. Do the science necessary to address criticism, justifiable criticism of the science. Work on important problems, not safe ones. At the time of the second assessment report, when all kinds of unpleasant things were happening to me, I seriously considered giving up science altogether. Steve encouraged me to continue. He said, "A measure of the importance of the work that you do is how many enemies you accumulate over your lifetime. And fingerprinting is important. You need to continue this work, Ben." And I'm glad he told me that. Similar lesson, don't be deterred by powerful opposition. Again, very relevant today. Never stop communicating the basic science, even in difficult times. We're in those difficult times today, and in my opinion, we have a responsibility to find novel ways of communicating our understanding of the reality and seriousness of climate change. Steve was particularly good at this. No matter how much you've risen in the firmament of climate science, always find time to inspire young scientists, to talk to them, to listen to them. He was brilliant at that. And show your passion for what you do. And again, I think you saw in the video just how good Steve was at showing his passion, his love for the science of climate change. So I mentioned earlier the 2.5 hours I spent looking at Steve's CV today. Here's a little word cloud that uses some of the keywords from Steve's papers and Steve's books. Look at the breadth and the depth of the things that he was interested in, from basic science, aerosol effects on climate, cloud radiative forcing, geoengineering, double attribution, so attributing changes in climate to human influence, and then looking at the difficult problem of it attributing changes in species to human-caused changes in climate. He was everywhere. And to me, this continues to inspire me to be a better scientist, to try and be a better communicator, and to continue teaching, as Steve did right up to the end, to continue listening. Thank you very much for the extraordinary privilege of asking me to give the 13th Schneider lecture, and I'd be happy to answer any questions that you might have.
So as Dr. Santer just mentioned, it is now time for the question and answer portion of the night. So will you join me over in these chairs?
Of course.
There's a glass of water right there.
Yeah, thank you.
So we have Sydney and Haley, both have microphones, and if any of you have any questions, please just raise your hand and they'll come over to you to ask your question. So to start, thank you so much for your speech. We really appreciate your words. Okay, let's start.
I jumped up because these are always slow to start. I'm Todd Besnick. I'm a computer architect. And right now we have some interesting things going on with generative AI, and you are trying to retire. How would you think about making a character.ai version of Steve Schneider so he can answer our climate questions?
Well, I'm glad you asked that question. I wish we did have a virtual Steve. We would need him urgently today. But I would say that AI is now a big thing in climate science. For example, the fingerprinting work that I described, there are people in my world who are using neural networks to try and disentangle human and natural effects on climate. There are a lot of things that neural networks and other clever algorithms can do in terms of processing huge volumes of data that are more difficult to do with traditional fingerprinting techniques. But they haven't fundamentally changed the story that I presented here. Just like you can train neural networks to recognize a dog or a cat, you can train neural networks to recognize this is natural climate variability, and then neural network, please separate human and natural effects on climate. And we're doing that. Lots of clever people are doing that. And these techniques are good at helping us to put error bars on the relative contributions of natural factors and human influences, say, to these satellite changes in temperature in the atmosphere. So I'm sure that many of the students in the room are spending a lot of time working on learning AI and applying AI to climate problems. There's some effort now to do weather forecasting with AI techniques, to actually train neural networks and other algorithms to make better weather forecasts. So we'll see where AI goes. My perspective is that it's always important to learn something about the physics of the climate system. I think that's what Steve, virtual Steve, would have told you. And a tool, if it can help you to learn something about the physics of the climate system, it's a good tool. If you're just using it in order to eat up CPU time, it's not a very useful tool.
Thank you for the question. I think we have one over here. Give it 1 second.
Hi, I'm Amy. I'm a second year, and you mentioned the Seam of Six model, and there's the SSP scenarios of the future, and I know there's like different variations of them, and I was wondering if you knew like how many models or like how many models they have to run in order to like compile that and put that into like the Seam of Six and like say that's like the scenarios that will happen, and I was curious about it. Thank you. Loved your talk.
Thank you for that question. So you're right, these scenarios, shared socioeconomic pathways or SSPs, cover the range from sort of business as usual to enlightened humanity, where we decide to reduce emissions of greenhouse gases rapidly after 2050. And modeling groups around the world performed simulations that go from the end of 2014 through to 2100 or beyond that look at the likely climate implications of following these different energy use pathways. And they're not just different energy use pathways, but also different pathways of population growth and technological innovation and collaboration between nations. So there are different storylines, if you will, about the future world. And we used results from SSP5 in the stuff that I showed you. So from the sort of intensive fossil fuel use scenario from 9 different climate models. Why only 9? Because for the stuff I'm doing, you need to have models that have tops right up into the stratosphere and have enough resolution in terms of the number of layers that enable you to probe what's going on in the stratosphere, hence the somewhat restricted sample of only 9 models. We hope that in the next phase of the coupled model intercomparison program, which is currently underway, there will be many more models that have that capability of providing us with information about not only what's happening at Earth's surface and in the troposphere, but also high up in the atmosphere, actually above the stratosphere into the mesosphere.
As an activist, I've put myself in situations where, doing conservative tabling, I've been met with people who kind of turn away from scientific data and like even when presented with these models, they shut down. So what is your advice on climate communication, on talking to people who just turn away from the science itself?
Great question. So since 1995, I was forced unwillingly to enter the public arena. I'm a very private person. I'm happiest when I'm far from the maddening crowd in the mountains climbing with my son. But my job as convening lead author of Chapter 8 back in 1995 put me in a position where I had to declare. This was the process we used to arrive at the discernible human influence finding. This was the nature of the then available evidence that allowed us to reach that finding. And I've had to declare since then. I've had to try and communicate complex science in simple terms, and that's hard. Steve was the best in the world at doing that, and I'm not Steve. And very few of us are Steve. But we still have a responsibility to try and translate complex science, as he did so effectively, into plain English, to tell stories, to get people to care about the kind of world in which their kids will live and love and hopefully thrive. So my strategy has been have laptop will travel. Wherever there are opportunities, like tonight's opportunities, I want them. I want to speak to audiences like the ones you describe, who are skeptical about me and everything that I do, and give them pause for thought. What are the consequences for you and everything you hold dear if you're on the wrong side of the science on this one? What does it mean? That's the best you can do in these times, to give people pause for thought. And as I said at the end of my talk, what we need to do is find novel ways of doing that communication and of scaling it up, taking individual voices and giving them power, making them bigger. There are folks out there, I don't need to mention names, who have megaphones that reach 200 million people. We don't have those kind of megaphones, but we have the science, and we have clear understanding of the reality and seriousness of climate change. We have a story to tell too. And like I tried to show tonight, that story is rich. It's internally and physically consistent. It's not a story that just arises from one model or one data set, surface temperature. Human fingerprints are pervasive in the climate system. That's the story we all need help in telling.
Hello, I'm Luca. Thank you for sharing your time with us today. You talked about your thought experiment where human behavior caused climate change well before we thought. Could you explain, before the Industrial Revolution, what kind of behaviors these were, and if that influences how you think about human-caused climate change now?
Well, great question. Let me take you back to 1860. So we have people like Eunice Foote and John Tyndall, who in the lab are doing the first experiments to try and understand the heat-trapping properties of CO2, water vapor, other greenhouse gases. At a number of large cities in Europe, we're starting to make measurements of surface temperature change. At the end of the 1800s, we have people like Arrhenius starting to construct very simple climate models and double and triple atmospheric CO2 and try and understand the sensitivity of the climate system to human-caused CO2 increases. Those were some of the drivers for this simple thought experiment. Humanity back then was putting it together, understanding that burning fossil fuels had consequences for our climate system, putting monitoring in place, at least in Northern Europe and America, that might inform us about the size and rate of changes. So I wanted to know then, given these simulations, how long would it have taken us? And that surprising answer, 25 years, I hope is helpful in communicating. What do I mean by that? There's this narrative out there that human-caused climate change is all Al Gore, and everything that we're doing is just motivated by Al Gore and IPCC, and that we really didn't know until recently that humans were affecting global climate. Well, we knew 30 years ago, I would argue at the time of the second assessment report, that we had formally identified a human-caused global warming signal. And what this new work shows is we could have known a long, long time ago. And the question again then is, would it have made a difference? We didn't have solar panels. We had some wind energy even back then. If we had known, would we have made different choices, better choices? I'd like to think that maybe we would have. But this Gedanken experiment, I hope, will help me to help us to communicate that the hoax conspiracy narrative never was credible. And it's even less credible now. There's nothing, no natural cause that can explain the changes we've measured and monitored in dozens of different elements of the climate system. That's the challenge for us, to convey that deep understanding. And we have a responsibility to do that every day, no matter what opposition there is out there.
Dr. Santer, thank you so much for your talk. It was fascinating. And one thing that you said that really stuck out to me is like the measure of the importance of the work that you do is how many enemies you make, and that matched up, I think, with what you described of the reaction to the second IPCC report. One thing I'm really curious to know is, in the face of that kind of opposition, like, how did you keep going? What kept you doing this work for 30 years after that?
People like Steve Schneider kept me going. I'm serious. Back then, in 1996, after publication of the second assessment report, a lot of bad things happened to me, not just professionally, but personally too. And I was seriously considering giving up science. Steve was so helpful to me, and Terry at that time, in telling me that this work was important. I didn't see that importance back then. I was just glad that the IPCC stuff was over and that I could get back to being a husband and a father and a scientist. I wouldn't have to go gallivanting around the world to attend IPCC meetings. But Steve and Terry helped me see that this work had to continue, and very powerful individuals and companies and even countries would try and destroy this work because they recognized what scientists didn't recognize back then, that this finding of a human influence on global climate was the scientific equivalent of the handwriting on the wall. It meant that ultimately we would have to change energy use and how and how much fossil fuels we burned. So what I've learned over the intervening 30 years is that that finding was really worth defending. It was worth all the difficulties, and the difficulties don't define who I am and don't define my life, I would say. What do I mean by that? When I speak to reporters, they often say, gee, your life sucks. So many bad things happened to you. And really, I had the extraordinary privilege of working with people like Steve and brilliant women and men around the world and working on issues that matter, disentangling human and natural effects on climate. That's extraordinary privilege. The bad stuff is background noise. So that's what I try and remember and hold on to in these challenging times, that I can still build, I can still add, together with my colleagues, brick by tiny little brick to the foundations of science, to our understanding of the nature and causes of climate change. There are many people on the other side who are destroyers. They can't build. And that's a fundamental distinction to me, the distinction between building and destroying. And all of you in the room, you can build. You can add to this edifice of science. That's something to hold on to, even in these challenging times.
Thank you so much, Dr. Santer. I'm very inspired by your talk, so thank you very much. As a student in climate science, I'm very curious to hear your opinion on what's next for climate change science and attribution science. You went from 1995, climate change being, the jury is out, and in 2021, it's now unequivocal that humans are impacting. But now what? Like, what's the next step for this field? Well, what should a young climate scientist do in 5 years, 10 years, 20 years? And most importantly, will it add anything to the conversation? We already know that it's unequivocal. So what's the point of more science?
Well, great question. And one of, Vannevar Bush had this report many years ago called Science, the Endless Frontier. And I would say that one of the frontiers in attribution science is impacts attribution. So looking at the, not attribution with human-caused climate change, but the impacts, say, on human health That's a big deal at the moment with changes in vector-borne diseases and extreme heat, trying to do fingerprinting with changes in human health. Another frontier, I would say, is event attribution. As you're probably well aware, over the last 5 to 10 years, there's been this shift from the kind of stuff I described, looking at changes in mean climate over decades, to looking at individual extreme events, at changes in intensity, duration, frequency, and trying to say something, trying to say, what do scientists know about the contribution of human-caused warming to changes in the statistics of those extreme events? The National Academy of Science is currently doing an update to a report they did about 10 years ago that will specifically focus on the state of knowledge in event attribution, another important frontier. AI, I think, is a frontier. How is it going to be helpful to us? Is it not going to be helpful to us? Will it teach us new things about climate variability and the response of the climate system to human-caused changes in sulfate pollution and greenhouse gases? Another frontier. So there are plenty of worthwhile problems for you and your peers to work on. The science, in my opinion, is not done and dusted. We have a lot of information about human effects on climate. That information is compelling, but there's still a lot to be done to understand how climate change is going to affect people. And one of the things that's very much a concern to me is sea level rise, tipping points. How close are we, something Steve was deeply concerned in, how close are we to nonlinearities in the climate system where bad stuff happens rapidly? Are current models fit for purpose, current Earth system models for looking at our proximity to tipping points? Do they need to be improved? Do they have missing physics, say, in the communication between ice sheet models and ocean models? We know we're not doing a very good job with certain things that may be critical to assessing how close we are to tipping points associated with sea level rise. So there are plenty of important problems for you and your peers to work on. Work on them with passion. Don't be deterred by these powerful forces of opposition.
For those in the room who are not familiar with tipping points, can you explain those a little bit more?
Sure. So a couple of tipping points have received a lot of attention recently. There's this thing called the Atlantic Meridional Overturning Circulation, which is this sort of vast flywheel in the Atlantic that is responsible for transporting warmer water from low latitudes in the Atlantic to higher latitudes, in part via the Gulf Stream, and then there's a return branch of this thing that goes into the southern hemisphere. And the concern is that as we increase greenhouse gases and warm up the Arctic, which is the driver of this flywheel circulation, and we change the salinity and the temperature structure in these key areas of the Arctic that drive this circulation, that we may slow it down. And that would have serious implications for Europe. Some of that warmth that is exported from the tropics to Northern Europe keeps Northern Europe more temperate than it would normally be. There's been a lot of reporting in the last year or two where folks have tried to calculate how close we are to a tipping point where this circulation might suddenly and perhaps catastrophically change. That's one thing. Another thing is the Amazon. Are we potentially getting close to tipping points through warming and potentially drying the Amazon, where we risk very rapid changes in the ability of the Amazon to draw down atmospheric CO2? And another, like I said, is sea level rise. We know that as we're warming the southern oceans, and warming the atmosphere in Antarctica and high latitudes of the southern hemisphere, we're melting back these floating ice shelves. These ice shelves buttress some of the land ice that would otherwise be free to flow into the Southern Ocean and to raise sea level. Some of these ice shelves have already broken up, like Larsen B. They've been there for many thousands of years. And many, getting back to the question about what to work on, lots of folks are interested in understanding observationally what's happening to ice shelves, and are they going to break up? How quickly, how rapidly will things like the Thwaites Glacier contribute to global sea level rise? And again, some of the physics that governs the communication between ice sheet models and melting ice and ocean models and changes in ocean circulation, we're not there yet. We don't have it. That's critical if we want to understand how rapidly and by how much global sea level is likely to rise over the 21st century and beyond.
Thank you. I think we probably have time for about one more question from the audience.
Hi, I'm Skylee. I'm currently a senior here at Stanford, and I'm not a scientist, and I've never really been super in-depth in the works of scientists, especially regarding climate change. But I'm very much a person interested in policy, and I was wondering, how has your connection been with policymakers, especially with how controversial your topic is, especially with the current administration? And I was wondering, how has your relationship been with them, and what are the recent developments you've seen?
Well, I've had opportunities to brief policymakers in Congress. It's tough to gauge whether those efforts were successful or not. Hearings are often some kind of elaborate kabuki theater where folks aren't truly interested, or at least some folks aren't truly interested in expert advice and guidance and in what people know. It's more an opportunity to grandstand and cast doubt on the science. Nevertheless, we have to continue to do that. We have to continue to try and reach policymakers on both sides of the aisle and educate them about the science and about, say, the government agencies that are involved in the science. NOAA, the National Oceanic and Atmospheric Administration, is a case in point. Why? The atmospheric temperature data that I showed you today, NOAA satellites, the original model calculations from Suki Manabe and Dick Weatherald in 1967 that showed warming low down and cooling up high, NOAA Research Lab. There's real concern that the data may go away, that the satellite measurements that have been collected for 40 plus years may not continue, that the evidentiary chain that enabled me to show you the kind of things that I showed you, satellite temperature changes right up to the present, that chain may break. That's of concern, and we have to educate, I think, our government about the value of information. Why is this stuff important? It's important for evaluating climate models, for understanding how and why our world is changing, and for weather forecasts too. Some of the satellite measurements that I talked about today are assimilated in weather forecast models and give us better weather forecasts. The value of this information is extraordinary. And as scientists, we have to make that case to policymakers that the worst thing we could do would be to fly blind into the coming decades. So that's what I want to do. I want to continue to make that case as Steve would have made it, or virtual Steve would have made it, we have that responsibility to say why this kind of stuff has to continue, why it's important.
Just as a final quick question, how do you remain hopeful in these times? Do you have advice for the rest of us out here?
Well, I have this daily practice of going to an overlook where I live in Southern Oregon that looks down onto beautiful Upper Klamath Lake. I go there almost every day, and I see this landscape, this horizon of mountains and lake and beautiful ponderosa pine forests. It keeps me grounded. It helps me to recognize that there are so many things of beauty in this world that we have to fight for, that we have to preserve. I don't want to give that stuff up without a fight. And I'm hopeful because I think everyone, irrespective of political persuasion, recognizes that we only have one planet here, and if we screw it up, our kids and grandkids and many future generations are in deep trouble. That makes me optimistic. It makes me optimistic after today that there are students, I met with many of you today, who want to make a difference in the world, who've chosen this career path with understanding that it's not the easiest career path or one that's going to lead them to wealth necessarily, but it will lead them to extraordinary scientific adventures, and they'll be working on things that really matter to other people. All of that, seeing young people who still want to do the basic science makes me hopeful, makes me optimistic. And I'm also optimistic because despite the current political environment in the United States, the science continues in the rest of the world. There are folks who are doing measuring and monitoring and modeling and will assume leadership, if we don't, of model intercomparison programs and model evaluation. The rest of the world understands that this work is important and has to continue. That makes me optimistic. And it makes me optimistic that there are individuals who are using their voices. Unfortunately, many of them have just lost their jobs. And they're speaking out. They're speaking out on LinkedIn and other platforms and sharing their stories about the value of the work that they did with NOAA or with EPA or with USGS or other organizations. There's a whole new generation of communicators out there. That makes me optimistic too.
Thank you for your response. Okay.
Thank you so much for your insightful words and for taking the time to travel here to join us tonight. Can we have another round of applause for Dr. Ben Santer? We would also like to thank everyone who made this lecture possible, including the Woods Institute and, of course, Terry Root.
Lastly, we wanted to say thank you for all of you for joining us and for providing such insightful questions. I didn't even really need to prepare any myself. You guys kept it coming. We really appreciate you taking the time out of your busy schedules. We know that it's a school night for a lot of you, and we really hope that you have a wonderful rest of your night. Thank you so much.
Thank you.